All right, so let's just wait 2 more minutes for the others. Am I muted? Ano? All right, so while waiting for the others, let me just edit this one so I can send it already to you guys. Nothing happened. Module 11 and module 12. And this one, all right. So regarding with the module 11 and 12, so we will not be able to discuss this one anymore since we don't have enough meetings left. And yeah, one more thing is this will not be part of your final exam anymore. So again, as a reminder, so your exam, final exam will be composed of four modules only. The Thevenin's theorem up to the delta to y and y to delta transformation. Okay, just those four. So I'll send those two modules later on, or I'll just upload it right here so that everybody can access that one. All right, so there you go. Okay, so before we start with the module 9, do you guys have any concerns so far? Or were you guys already there? Wala pa? Wala pa kayo dyan? Can you guys give me a thumbs up if you guys are in front of your PC already or smartphone? Okay, so 1, 2, 3, 4, 5, 6, 7. All right, very good. So nandiyan naman pala kayo eh. Why are you guys not speaking or responding? Anyway, So for the source transformation, so just a very short description. So source transformation. So if you have a current source, so you can transform that one into a voltage source. So vice versa, if you have a voltage source, then you can also transform that one into a current source. Okay. So just a background study regarding source transformation. So it's an electrical network can consist of sources and passive elements. Okay, so the passive elements are the resistances, okay, the capacitance, etc., etc. Sources are circuit components which possess their own energy and are capable of transferring this energy to the other circuit elements. So there are two basic types of sources. We have the voltage source and then the current source. So this can be further classified as independent or dependent. So the one that we are always using is independent. So for the first time, okay, in our course, we're going to use dependent. So basically, when we say dependent, it's depending on the other, let's say, component. Say we need to have the current before we can solve the voltage for that dependent source, something like that. Okay. So in the case of independent sources, the voltage or current is fixed. So it is a fixed value. But independent, the value of the voltage or current depends on the amount of current or voltage elsewhere in the circuit. That's why it's called dependent. Okay, and then we have the passive components. So they don't have their own energy. So as a result of this, they are regarded as sinks. However, they influence the amount of current voltage in a given portion of their circuits, like resistors, capacitors, inductors, uh, and many more. Okay, so we have any other passive components. So those are just the uh, famous, okay, passive components. All right, so skip this one. I'll leave the reading part to you guys. Okay, so here are some of the list of the important theorems along with a brief explanation. Okay, so superposition theorem is good in finding current voltage, wherein it has multiple sources. And then Thevenin's theorem and then Norton's theorem, okay, they are the best when it comes to complex circuit, okay, when it comes to transforming it into a very simple circuit. Again, for the Thevenin's theorem, we have the Thevenin's voltage and then a resistor. Okay, for the Norton's theorem, we have a current source and, of course, a resistor also. So they are the same when it comes to resistance. And then for the Millman's theorem, so this one is a simplification technique involving circuits with parallel branches. So this one is good when we have so much parallel branches. So at this point, it should be noted that all of these theorems are based on the basic rules governing the field electronics, namely Ohm's law, okay, and Kirchhoff's law. So that is why if you wasn't able to get the concept of Ohm's law and Kirchhoff's law, then you won't be able to solve the Norton's theorem, Thevenin's theorem, superposition, Millman's, and many more. Okay, and then the next one is the delta to y and y to delta. Okay, the one that is actually the module 10. Okay, the one that we will not be able to discuss anymore, but again will be a part of your final exam. So that is the only assignment that I'm asking you guys to study. Okay? So please do a self-study regarding with that one. So I'm really sorry since we don't have enough time anymore. And yeah, so anyway, delta to y or y to delta is a super easy method or theorem. So you'll be able to learn that one real quick. Anyway, so we have this example right here. Okay, so the goal is to find the current denoted by I. So we have to find the current right here. Okay, what is this current that is flowing here? So yes, we have a current source that is 1 amp. So some of the currents will flow on this node or on this node or sorry, on this branch. Okay, that's the correct term. On this branch or on this branch or on this branch. Okay, so one way that we can do is eliminate this one and convert this one from current source into a voltage source. So how are we going to do that one? So in here, if you're going to convert a current source, okay, of course you need a resistance. That's because, okay, let me borrow this one again. Let's go back to the original circuit. Okay, so as long as you have a resistance on it, okay, so in here, going back with our Ohm's law, okay, so V is equal to I times R. So in here, we have a given current, we have a given resistance. So if you're going to convert a current, okay, current into a voltage source, okay, so this current, okay, current circuit must be in parallel with each other. So what do I mean by they are in parallel? So the current is in parallel with the resistance, okay, I and R. So that's one way for you to be able to check if it's possible to convert a current into voltage, okay? And then of course, once you have converted this current to voltage, it will now become a series connection, okay? And then retaining the resistance, okay, which is now in series connection. All right. So again, just apply Ohm's law. V is equal to I times R. So V is equal to 1 amp times 10 ohms. It will give you 10 volts. Okay. So that's how we've got these 10 volts right here. And one more thing, for you to be able to know the polarity, okay, so wherever is the current is flowing, okay, so from here, okay, it's flowing in there. So this one is the positive polarity, and then the tail is the negative polarity. That is why if you're going to convert this one into a voltage source, this is your positive and then this is your negative, which is now the same with this one. And at the same time, we have retained the resistance, okay, which is still 10 ohms, but they are now in series connection. All right. So were you guys able to follow at this point?
Yes, sir.
Okay. So again, if you want to convert the current source into a voltage source, it must be in parallel connection. So once you have converted that one into a voltage source, it will now be in series connection. Okay. So vice versa, if you want to convert a voltage source into current, okay, so this one must be in series connection, and the other one, once you have converted the voltage into current, it will now become a parallel connection. Okay, so basically, this one is vice versa. Okay, current to voltage, voltage to current. Okay. Okay, so from here, voltage to current transformation. So, okay, we have simplified this one a little bit more, wherein we were able to add those two resistance, the 10 ohms and 5 ohms. The 5 ohms, okay, which doesn't have anything to do on the other side. Anyway, so just this one, okay, wherein we have added the 10 ohms and then the 5 ohms right here, and then the left side still remain. But then again, you can simplify this one into something like this, okay, wherein we have the resistance 5 ohms and then the voltage source 10 volts, and then the voltage source 10 volts on the right side, and then the 15 ohm resistance. So from here, you can actually apply the superposition theorem. I think I have mentioned that one in here. No, sorry. But yeah, you can apply superposition theorem in here for you to be able to find the current. Okay, since we have two voltage source. Or you can apply mesh analysis, which what we did in this example. Okay, so in here, where is the solution? What is the next one? All right, so it already mentioned here that we can already apply mesh analysis for us to be able to find the current, but you can, apply again another transformation. Okay. However, there is also a much easier graphical way of achieving this, wherein apply source transformation again. Okay. So that is why in here, from a voltage source, we can have a current source. Let's copy that one. Okay, so from here we can transform this voltage source again into a current source. So again, if we have voltage and then you want to convert this one into current, okay, so the voltage circuit must be in series, and then the current transformation will now become parallel. Okay, so yeah, as you guys can see right here, it is in series. It is also in series, which is made as possible to convert this voltage source into a current source. So as always, the one that we are saying when it comes to in series is the resistance value. Okay, so if it's a current source, it must be in parallel with resistance. If it's a voltage source, it must be in series with resistance. Okay, so the same with that one. Okay, so basically that's the logic behind source transformation. Okay, now from there we can already solve this one. So from voltage to current, so we need the formula of current. So I is equal to V divided by R. So V is 10 volts and then R is 5 ohms. So 10 divided by 5 is 2. So we have 2 ohms. So if you're going to transform this one, we will have a parallel connection. So again, wherever is the polarity, I mean the positive polarity, that is where the direction of the current will go. So we have now the current source, and we now have a parallel connection. Okay, so it will still retain the value of your resistance, which is 5 ohm. Okay, and then the middle part will stay the same. And then on the right side, of course, if you're going to convert this one into, a current source, so the same, it will become parallel. So we have 15 ohms right here, 5 ohms right here, and then a current source. So this is 2 amps. So for us to be able to get the value of this one, so apply Ohm's law, V divided by R. So V is 10 volts divided by 15 ohms. So it will give us 2/3. So we have here 2/3. Okay. So were you guys able to follow on how did we transform this one into something like this? Hello, were you guys still there? Again, if you want to
Hindi
convert
ko
a
po, sir.
voltage source, ano yan?
Sir,
Yes?
sabi ko sir,
Huh?
andito pa.
Andyan pa. Okay. So were you able to get this one, Mr. Gangas?
Yes, sir, yes.
Sure. Again, I only have this graphical representation. This is your basis when it comes to transforming a source. So again, for you to be able to transform a voltage source, it must be in series connection. And then, of course, from voltage, it will become current. But once you have transformed that, that voltage source, it will become parallel in connection. Okay, that is why we now have a parallel connection for the resistance in here. So that's how we've come up with this uh, figure in here. Okay, and then from here, you can actually already add those two. So if I'm not mistaken, let me just check. 2, 3 plus 2. So yeah, since we have two current source, let me get that one. since we already have two current source in here, okay, 2 amps and then 2/3 amps, okay, so they will meet on the node X. So they have the same flow of current, so they will symmetric with each other. So 2 amps plus 2/3 is equal to 8/3. Okay, are we correct? Okay, which is 8/3 ampere. So yeah, there you go. We already have solved the current that is flowing in here. Okay, so the one that we did is, by purely uh, using source transformation. Because in step 2, if you're going to apply mesh analysis, yes, you will also be able to get 8/3. However, that one is already combined with other method. But if it's a pure source transformation, then you can do this one. Okay. All right. So from there, there are 3 resistors, 2, 5 ohm resistors. Sorry. So we are not yet done with our goal. Actually, our goal is to find the current through the 5 ohm resistor. Okay. The one that we did, okay, is just get the final, the total current, okay, which is the 8/3. Okay. So that is the total current. So the one that we need to solve is the current or the individual current that is flowing on this node X. Okay. So from here, we can actually combine the 3 resistance, the 5 ohms, 5 ohms, and then 15 ohms. So just, apply parallel formula for the parallel connection of those 3 resistance. And then you will get 15/4. All right. And then from there, we will have the simplified circuit. Okay, so what else that we did in here? Okay, so from here, we have transformed this one again. So this is the third transformation now. Okay, so we have transformed the current into a voltage source. Okay, so again, if it's a current, it must be in parallel. And then once you transform that one into a voltage, it will become, call this one a series connection. And then the value of your resistance will retain, which is 15/4. And then from here, we can already apply KVL. Okay, just one loop in here for you to be able to get the value of I. So having that one, let's solve this one with our own solution. So apply KVL. So we have positive 10 volts minus I times 15 divided by 4 minus 5 times I equals to 0. Okay, so from here, we can combine those two. So 10 minus 15 divided by 4 minus 5. It's also negative. So we have negative 8.75 I is equal to 0. So from here, you can now transfer this one on the other side, or just get the I itself. I is equal to 10 divided by 8.75. So 10 divided by 8.75 will give us 1.14 amps. Okay, so this is the current that is flowing on this node X, or this 5 ohm resistor. So let's check. We have here 8/7. What is 8/7? 8/7 is, all right. So we have the same answer, which is 1.14 amps. Okay, so just apply KVL, and then you will get the current that is flowing here already. All right, so were you guys able to follow this one? So we have applied a total of 3 transformation. So if we are going to compare this one, so from these, from this to that, okay? So see, we have a complex circuit, but using source transformation and then another source transformation and then another source transformation, we can arrive with this circuit, okay? Which is, similar with Thevenin's equivalent circuit. It's a different method. Anyway, so I made this one super easy to understand. So if there is a part that you guys didn't understand, so you can always go back on this presentation and yeah, just read it again and then try to analyze. And then if you cannot understand it, if you are super confused, so feel free to message me. Okay, so we can have a short Zoom meeting. Okay, if you are really confused and needs help. Okay, so yeah, we can have a one-to-one Zoom meeting. Anyway, let's have another example. But right now with the use of dependent sources. So let me just tell you guys this one. So how will you know if that one is a independent, okay, or dependent uh, source? So one thing that you can see if it's independent is it's always being represented by a circle uh, drawing or circle diagram, okay? But if it's dependent, it's always being represented by a diamond. Okay? And then mostly, this voltage, let's say this one is a voltage source, this one is also a voltage source. But for you to be able to get the voltage source, okay, this one has, ano ba? Yeah, I think something like that, 5i, okay? So we have a connected resistance here, wherein you see 10 ohms. And then before you can get the equivalent, okay, circuit of this one, it's being dependent to our current that is flowing in this circuit, okay, which can be solved by the other connections right here, okay, or right here, depending on circuit. Okay, so it is something like this, wherein we have this circuit. So source circuits, dependent sources. Okay, so I guess we have the same uh, goal. We have the same goal, yes. So the one that we need to find in here is the current that is flowing in here. Okay, so from here, actually you can separate those two by having this one. Okay, so from here, we have a 3 current that is flowing on this 1 ohm, the same with 2 ohms. So you can do this one, okay? Because if you're going to analyze this one, we have a series connection right here, okay? Wherein this one is also connected right here. So you could say that the current that is flowing on this side is the same on this side, okay? So 3 amps and another 3 amps right here. So from there, we can now easily convert this one, okay, current source into a voltage source. So again, just apply what the concept or what you guys have learned. So if it's a current to voltage, so it must be in parallel. And then once you have converted that one into a voltage, it will become series. Okay. So once you have solved that one, you will come up with this connection. Okay, so let me just get this one and then compare if that's the transformation. So from this to this. Okay, I'll not erase that one anymore. So again, we need voltage. We need the formula of VIR. So I times R is 3 times 1 is 3 volts. And then 3 times 2 is 6 volts. And then again, just follow the polarity. So positive to positive. Oops, this one, the arrow means the positive, and then the tail is negative. All right. And then the next thing that you can do is you can even separate those into three. So we have a series connection for voltage, series connection for voltage, and then series connection for voltage. So from here, you can apply again source transformation into a current source. Okay. So from there, what is the next one? Voltage source. 5i times 5, 3 volts plus 3, and 5 ohms plus 6 volts. Where did we get this 5 ohms right here? Sorry. So I forgot to add this one. So before you can come up with this one, okay, so from here, you have to add those two resistance. Okay, so 1 ohm plus 2 ohm. That is why we have here 3 ohms in total. Okay, so the same with this one, you have to add the 2 ohms plus 3 ohms. That's why we have 5 ohms in total here, and then 3 ohms in total here. And then their voltages remain. And then from here, you can convert this one again, into a current source. So here are the computations. So I will not copy this one anymore. So this is already the stage 3, okay, transformation. So this is already your third transformation. So from series will become parallel, okay, and from here, okay. So what did we do next? Okay, so from here we have added, okay, the bottom one and then the upper current source. Since they have different flow of current, so the other one is going to the right, and then the other one is going to the left. So you have to, where is that one? 6 divided by 5. So you have to deduct the other current source. So whichever is the bigger one, that is the dominating current. Then whichever is the lower one is of course this will be deducted. Okay, so we have here the current. So 6 over 5 minus 1 is equal to 1 over 5 amperes. Okay, so from here, we already know that the current that is flowing on this I1 right here on the dependent source is 1 over 5. So we can already use 1 over 5 to add on this I1 to get the total current that is flowing on the entire circuit, which will give you this simplified equation. Okay, so we have already combined the resistance, the 5 ohm and then the 3 ohm. So just do the parallel solution, will give you 15 divided by 8. And then this newly formed equation coming from this combined current. Okay, so what's next? Transform the time source. All right, so from here, we have again applied another source transformation. So this is, I think, the fourth source transformation. So from current, it became a voltage source, which will give you this equation. Okay, so I will not show to you guys the step-by-step solution anymore. So supposedly, this one is super easy. However, we don't have enough time anymore, so that is why I am in rush in explaining this one. But yeah, this is already the fourth transformation, and then you will have this series connection right here. And then from there, you can already apply KVL, okay? And then you will have this equation or solution, and then you will arrive at 3 over 40 amps, okay? So that is already the current that is flowing on our I1. Okay, so as a conclusion, source transformation, okay, this one first. The analysis presented in this article on source transformation can be summarized in the following 3 points. So the first one is source transformation carried out per the rules shown in figure 14. Okay, so right here we have a series connection will become parallel connection. And one thing that you need to see also is the polarity. Okay, the polarity here is positive, so we have to change the direction also. So wherever is positive, that is the direction of your current. And the other one is we have a voltage source into a current source. Oops, sorry. That is just the representation of dependent. Okay. Anyway, again, the logic that we are trying to come up before is voltage source to current. So we have series in here and then parallel in current source. So that's always the logic behind source transformation. Okay, and yeah, so dependent sources can be transformed just like independent sources. And then lastly, the technique of source transformation can be even be used to analyze circuits which have capacitors and inductors, and provided we analyze them in the frequency domain. Anyway, so since we don't have that enough time anymore, so I guess I will end our meeting now in here. So if you guys have question, so please message me. I know that I have many what is the English of pagkukulang. So marami akong pagkukulang sa inyo. So feel free to message me anytime, okay?